Assalamu alaikum. My dear cadets of class 12, I welcome you all to my online physics class of Virtual Cadet College. During this ominous cloud of COVID-19, you are not able to stay at your second home. COVID-19 is a curse for human being. That's why our academic program is being hampered. That's why this online effort that has been taken by the authority of Virtual Cadet College, I think this program will be very much helpful for all of us. We are passing through a very rough and tough situation due to corona outbreak. There is no doubt. So stay home, stay safe, and try to follow this advice that inserted here. Before commencing my class, I would like to introduce myself. This is Kamrul Jaman Khan, lecturer, Department of Physics, Borishal Cadet College. This class for class 12, subject physics, chapter 4, and it is symbolized by magnetic effect of current. You know it very well that it is our continuation of our previous classes. So this chapter is running, no more delay here. Today's topics are, I already have discussed about Hall effect, torque in a magnetic field, but today I will discuss terrestrial magnetism, magnetic materials, and hysteresis loop. Learning outcomes. By the end of my today's discussion, cadet, you will be able to explain Hall effect and torque acting on a current loop in the magnetic field. Describe the magnetic field generated due to the rotation of electron in the orbit and magnetic field produced due to electron spin. You will be able to explain terrestrial magnetism and its components. And finally, you will be able to explain with graph of hysteresis loop. Key points of my today's discussions are inserted here. Please have a look. Okay, my dear boys. Today I am going to discuss about the terrestrial magnetism part. No more delay here. Okay, let's see. Look at this figure. This is our magnetic meridian and it is geographical meridian. This is geographical equator and it is magnetic equator. Okay, let's see some terrestrial related parameters. Geographic axis. Geographic axis is a straight line passing through the geographical poles of the Earth. It is the axis of rotation of the Earth. It is also known as polar axis. Geographic meridian. Yes, this is our geographic meridian. Here, I should better say this is the north pole of geographical meridian and this is south pole of geographical meridian. It is also known as true north and it is also called true south of geographical meridian. Geographic equator, yes, this is our geographic equator and it's a great circle on the surface of the Earth. Magnetic axis, okay. Please look at this. You know it very well that this is a bar magnet and I am drawing 2 points here. This is North Pole and this point is symbolized by South Pole. Okay. A line passing through this point is called magnetic axis. Is called magnetic axis. Okay. Magnetic meridian. Magnetic meridian at any place is a vertical plane passing through the magnetic north and south poles of the earth. Yes, this is our magnetic meridian. Boys, our concern is to discuss here that the magnetic meridian and geographical meridian are not coincide here, okay? Are not coincide here, and it is very much clear to us that there is a deflection between this geographical meridian and magnetic meridian, and this deflection is known as another parameters, that is declination. Okay, let's see a video. I think after observing this video, each and every parameters that's related, that is terrestrial related magnetism parameters, every parameters that's related terrestrial magnetism will be very much clear to all of you after observing this video. Please have a look.
The Earth's magnetism, or terrestrial magnetism. In 1600, William Gilbert, who was a physician to Queen Elizabeth I of England, showed that the force acting on a suspended magnet is not due to the influence of the pole star, but to a magnetic field which is present all over the surface of the Earth, as if the Earth was magnetized. Gilbert made a large spherical ball from magnetite, the poles of which were situated on two opposite ends. By placing a small magnetic compass on this magnetite sphere, Gilbert showed that the compass took up a definite direction at different points on the sphere as it does in the case of the Earth. According to his view, the magnetic field on the surface of the Earth can be approximately represented as if caused by a huge imaginary bar magnet in the interior of the Earth, but inclined to the geographic north and south axis of the Earth. This concept of terrestrial magnetism has been illustrated as shown in figure. The north end of the imaginary magnet has a south polarity, while the south end possesses the north polarity. Declination. In order to understand the term declination, let us first define two terms: geographic meridian and magnetic meridian. Geographic meridian at any place is a vertical plane passing through the geographic north and south poles of the Earth. Magnetic meridian at any place is a vertical plane passing through the magnetic north and south poles of the Earth. The angle between the magnetic meridian and the geographic meridian at a place is known as declination or variation. In figure ABCD is the magnetic meridian, and AB-C-D- represents the geographic meridian at a place. The angle BAB- is equal to theta is the angle of declination. The angle of declination varies from place to place on the Earth's surface. Gilbert believed that the declination at any one place was constant in time. But this belief was soon proved wrong. There were several periodic variations in the value of declination for a given location. Dip. A magnetic dipole suspends freely at its center of gravity so that it can rotate about a horizontal axis. Suppose dipole takes up the position as shown in figure. The angle through which the end pole dips down with reference to horizontal is called the angle of dip. It varies over the Earth's surface. The places where the dip is 90 degrees North Pole down and 90 degrees South Pole down are called the magnetic poles of the Earth, generally denoted as NM and SM. Along a line called the magnetic equator, which runs somewhere near the equator, the dip is 0. Horizontal component of Earth's magnetic field. The total intensity of the Earth's magnetic field does not lie in any horizontal plane. Instead, it lies along a direction making an angle delta, angle of dip, to the horizontal. The intensity B bar of the Earth's magnetic field can be resolved into two rectangular components. 1. The component in the horizontal plane is called the horizontal component BH, or simply H. 2. The component in the vertical plane is called the vertical component BV, or simply V. As is clear from figure, tan delta is equal to BV by BH. Cos delta is equal to H by B. Sin delta is equal to V by B. Now, cos square delta plus sin square delta is equal to H square by B square plus V square by B square, or 1 is equal to H square plus V square by B square, or B is equal to square root of H square plus V square.
Okay, my dear boys, I think you will get clear concept, or you have got clear concept about the terrestrial magnetism. Now I'm going to discuss about the declination and the or inclination, that is symbolized by delta. Okay, the angle between the magnetic meridian and geographical meridian at a place is called the declination of the geographic magnetism. It is also called transition angle, and it varies from place to place. Suppose this is our figure, and this line is the indication of our geographical meridian, and this line is the indication of our magnetic meridian. Yes, here is a deflection that is defined by theta, and it is called declination. And since this declination is at the west side of this geographical meridian, so it is defined by somewhat degree west, somewhat degree west. Okay, let's see. Suppose the declination angle of Dhaka is half degree east. Yes, half degree east. This statement means that the axis of freely moving magnet makes an angle, yes, makes an angle half degree, makes an angle half degree with the geographical meridian, but it is our concern this geographical meridian will happen in which direction. Okay, with the this half degree angle is making with the geographic meridian from the magnetic meridian, and its north pole is in the east of the geographic axis. Its north pole, that is the pole of this earth magnet, is hanging towards the east, towards the east. Okay, it will be something like that. this is east, so this is our half degree, and it is towards the east of this geographical meridian. Okay. Now, angle of dip or inclination, the angle between the direction of the Earth's magnetic field at a place and the horizontal direction measured in the plane of the magnetic meridian is called the angle of dip of the geomagnetism of that place. Here, this is our horizontal axis. This is boys, this is our horizontal axis, and this is a string by with or with this string, this compass or bar magnet is suspended here, and this bar magnet is hanging here somewhat angle, and this angle is defined by delta, and this delta is called angle of dip or inclination. Okay, let's see. Yes, the angle of dip of Dhaka is 31 degree north. Yes, north means the north pole of this bar magnet that is suspended from a rigid position will hang towards the geographical axis. Okay. Angle of dip of Dhaka is 31 degree north means that if a bar magnet is suspended freely from its center of gravity, the north pole of the magnet will remain hanging downwards and its magnetic axis will make an angle of 30 degree with the horizontal. Okay, so it is very much clear to us that this pole is north pole of this bar magnet, and this pole is south pole of this bar magnet, and north pole will make 30 degree angle with the horizontal. Okay. Okay, horizontal component of Earth magnetic field. Yes, this is the geographic meridian, and it is our magnetic meridian, and the angle between geographical meridian and magnetic meridian is called declination, that is denoted by theta or alpha. And now I am going to discuss about the angle of dip here. This is our horizontal axis, and this is our vertical axis. Along this horizontal axis, this magnetic induction or magnetic field of Earth is divided into two parts, that is BH and BV. This BH is symbolized for horizontal magnetic component, and BV is symbolized for vertical magnetic component. Okay, let's see. BH is equal to B cos delta and VH is equal to B sine of delta. Now, from these two equations, we can get B is equal to root over BH square plus BVH square. This is our resultant magnetic field of Earth magnetism. Classification of magnetic field. Yes, boys, I think I have discussed all the parameters that are related about terrestrial magnetism. Now I am going to discuss about the magnetic material. Classification of magnetic materials. There are 5 types of magnetic materials: diamagnetic materials, paramagnetic materials, ferromagnetic materials, anti-ferromagnetic materials, and ferrimagnetic materials. Diamagnetic materials or substances are those substances which are repelled by a magnet. These are the example of diamagnetic substance. Paramagnetic substance also a magnetic substance, but these substances are attracted by the external magnetic field very feebly, and these are the example of paramagnetic substance. Magnetic domain. Before discussing about ferromagnetic material, we have to know magnetic domain. Magnetic domain is a region in which the magnetic dipole or magnetic dipole moment are placed. At normal temperature and in absence of external magnetic field, these domains are distributed randomly throughout the entire material. Hence, this net magnetic moment of the substance is zero. That's why in absence of external magnetic field, magnetic materials does not show magnetism. Here, this is our iron bar, and this iron bar is not placed inside of magnetic field, so the dipole moment of this iron bar are randomly distributed. Yes, this is our second figure. In this figure, this iron bar is placed inside of magnetic field or magnet. That's why this iron bar is transformed into a magnetic material, that is bar magnet. And here, due to the presence of magnetic field, the magnetic moment distributed in a uniform direction, and here this border is called magnetic domain, and these are the domain. This border is called domain wall. This border is called domain wall, and these are the magnetic domain. Okay, let's see this video. Okay, my dear boys, this is the simulation of magnetic domain. When there is no application of magnetic, or that is magnetic field, then this magnetic needle are distributed randomly. But when or once you applied magnetic field here, there is happening perturbation, and this magnetic compass are aligned in a uniform direction. I am repeating, this magnetic compass is the identical part of magnetic domain. This magnetic compass are the identical part of magnetic domain. Here, sorry, magnetic moment. Here, these magnetic moments are aligned in a uniform direction. So these are the magnetic domain. Okay, these are the magnetic domain. Yes, it is a magnetic domain. It is one of the magnetic domain, and it is also a magnetic domain. Now, ferromagnetic substance or material. Ferromagnetic substance or material are attracted by the presence of magnetic field strongly, and it can be magnetized very easily. So, these are the example of ferromagnetic substance. Now, I am going to discuss about ferromagnetism, anti-ferromagnetism, and ferrimagnetism. Okay, here you can see that this is the spin of this magnetic material. This is the spin of this magnetic material. The spin of these magnetic materials are aligned in a uniform direction, that is in a same direction. That's why the net magnetic moment is very high. So ferromagnetic materials shows the magnetism, very strong magnetism, shows the very strong magnetism. Here, anti-ferromagnetism, regular alternating alignment of neighboring spin. Yes, the electron spins are aligned here, alternate way. That's why the net magnetic moment of this substance is zero. That's why this is called anti-ferromagnetism. Here, I'm going to discuss now ferrimagnetic material, anti-parallel alignment of unequal electron spin. Yes, the electron spins are unequal and these electron spins are anti-parallel. So the magnetic moment, net magnetic moment is not so high, but there must have magnetic moment. And the example of ferrimagnetism or ferrimagnetic material is ferrite. My dear boys, this is the chart for the comparison of diamagnetic material, paramagnetic material, and ferromagnetic materials. Please have a look towards this chart. I think you have got clear concept about dia, para, and ferromagnetic materials. So please have a closer look towards this chart. Yes. Let's have a closer look towards the video of magnetic material.
Different types of magnetic substances. When we bring a piece of iron closer to a magnet, it gets attracted towards the magnet. Iron and steel are not the only substances which are attracted by a magnet or which can be magnetized. In fact, most of the materials are magnetic. Michael Faraday, an English physicist, classified the magnetic substances into three classes, namely diamagnetic substances, paramagnetic substances, and ferromagnetic substances. Click on the links to know more about each. Diamagnetic substances. Diamagnetic substances are those substances which are feebly repelled by a magnetic field. Bismuth, lead, mercury, copper, diamond, gold, silver, and silicon are examples of diamagnetic substances. If a lead rod is suspended in a magnetic field, it slowly sets itself at right angles to the direction of the field. The behavior of a diamagnetic substance is independent of temperature. Paramagnetic substances. Paramagnetic substances are those substances which are attracted by a strong magnetic field. If an aluminium rod is suspended in a magnetic field, it slowly aligns itself along the direction of the magnetic field. Aluminium is an example of a paramagnetic substance. Aluminium, platinum, chromium, magnesium, tungsten, and calcium are paramagnetic substances. A paramagnetic substance, when placed in a magnetic field, is feebly magnetized in the direction of the magnetizing field. Temperature has an adverse effect on a paramagnetic substance. Due to rise in temperature, a paramagnetic tends to lose its magnetism. Ferromagnetic substances. Substances exhibiting strong magnetic properties are called ferromagnetic substances. Iron, cobalt, nickel, steel, alnico, etc. fall under this category. If an iron rod is suspended in magnetic field, it quickly aligns itself along the direction of the magnetic field. A ferromagnetic substance, when placed in a magnetic field, is strongly magnetized in the direction of the magnetizing field. Temperature has an adverse effect on a ferromagnetic substance. Due to rise in temperature, a ferromagnetic tends to lose its magnetism.
Okay, my dear boys, I think you have got clear concept about magnetic material. Now I'm going to discuss about hysteresis loop. Now I'm discussing about hysteresis loop or magnetization curve. After magnetizing a ferromagnetic substance by applying a magnetic field, then to demagnetize it, if the applied field is withdrawn, it is seen that it does not demagnetize easily. The way the magnetism of the substance increases while applying a magnetic field, the magnetism does not decrease in the same way while the magnetic field is withdrawn. This apathy of demagnetization of the magnetic substance is called hysteresis. Let's see. Yes. Look at this my drawing. Let us suppose it is a iron bar. And this iron bar is placed inside the magnetic field, that is external magnetic field. Suppose this is our external magnetic field. So due to the application of external magnetic field, this iron bar will get demagnetized. But when this iron bar is replaced from the external magnetic field, suppose this is the iron bar and there is no external magnetic field. So at this situation, this iron bar will not demagnetized very easily. I am repeating, this iron bar will not demagnetize very easily. It will take some time. That is, it shows disapathy to demagnetized, and this is called a hysteresis loop. This is called hysteresis loop. Okay, let's see what is hysteresis loop. Suppose this is our magnetizing force. It is applied along the x direction, and it is our magnetization. It is side along the y direction. Now, while we are increasing the magnetic force, the magnetization is increasing, and it is reached at a point. After reaching this point, look at this point. After reaching this point, the magnetization will not increase. The magnetization will not increase. It is called saturation point. Suppose it is our A point. This is saturation point. But it is our concern when you are going to remove this magnetizing force. It is supposed to get the demagnetization along this line. It is supposed to get the demagnetization of this iron bar along this line, but will not get. This is the dissipathy, and it is symbolized by hysteresis loop. Okay, let's see. Okay, intensity of magnetization increases with the increase in magnetizing force, that is A's, initially through OA and reaches saturation at A. This is our saturation point. And when A's is decreased, I decreases, but it does not come to zero at A's is equal to 0. That is, while A's is 0, but I is not 0, but it is supposed to be. Okay. This residual magnetism set up in the material represented by OB line is called retentivity. This OB line is called retentivity. It is our very interesting part, that this OB, from this OB, it is called retentivity. Okay, this is called retentivity. That is residual magnetization while magnetic force is 0. Okay, to bring I to 0, that is, we are talking about the demagnetization completely of this iron bar or ferromagnetic material. Opposite or negative magnetizing force is to be applied. This magnetizing force represented by OC is called coercivity or coercive force. This OC is called coercivity or coercive force. Okay, coercivity or coercive force, this is OC. Okay, here we are getting our H 0, but sorry, here we are getting our H at a negative value, but magnetization, that is I, is 0. Okay, but it is supposed to get, when H is equal to 0, I should be 0. Okay, but really we don't do it, or we don't get it as like this. Okay, for ferromagnetic material. Okay, let's see our next part. After reaching the saturation level D, it is our saturation level. This saturation level for negative value, and this saturation level for positive value of magnetizing force. When the magnetizing force is reversed, the card closes to the point A, completing a cycle. That is O, A, B, C, D, E, F, A. It is our complete cycle, but we are talking about hysteresis loop, so that's why we'll not get our origin. We'll get point A, B, C, D, E, F, and A. This is a loop, and this loop is called hysteresis loop. The area of the loop gives the loss of energy due to the cycle of magnetization and demagnetization successively, and this energy is dissipated in the form of heat. Now, what is our concern, or what is our aim to discuss about hysteresis loop? Yes, from the hysteresis card, we will get very easily our temporary magnet and permanent magnet. This hysteresis loop will show the property of temporary magnet and permanent magnet. Okay, let's see. The material like iron having thin loop is used for making temporary magnets. Okay, thin loop, that is the materials who is posing higher retentivity, whereas please. The material which possessing higher retentivity are used to build up or used to make a temporary magnet. Okay, and the material who is having or pose higher coercive force than that of retentive force or retentivity. These materials are used to make permanent magnet like steel. Okay, okay, let's see a video. After observing this video, I think your concept about hysteresis loop will be very much clear.
Hysteresis curve. We consider a ferromagnetic material inserted in a solenoid. Initially, both H and B are zero. We increase H by increasing the current. The magnetization and hence B increases to its saturated value as shown by the segment AB. We now decrease H to zero. B does not retrace its original path but follows the path BC. The value of B at point C when H is equal to zero is called retentivity. If we reverse the current, we reach the point D at which B is equal to 0. The value of H at point D when B is equal to 0 is called coercivity. As we further increase the reversed current, B saturates in the opposite direction at point E and turning the current to 0 at point F. If we increase the current, B again gets saturated value at point B. The path BCDEFGB can be repeatedly followed. The closed curve BCDEFGB, which represents a cycle of magnetization of a ferromagnetic material, is called its hysteresis loop. Hard ferromagnetic materials have large coercivity and are characterized by broad hysteresis loop. These materials are used to make permanent magnets. Soft ferromagnetic materials have small coercivity and are characterized by narrow hysteresis loop. They dissipate less energy when they are cycled through a hysteresis loop. They are used in devices such as transformers.
Okay, my dear boys, now I am going to discuss some problem. Let's see. This is the stem. This is the stem, and here three questions are stated. Let's see. Find the magnetic field at point A. Yes, I'm talking about the magnetic field of a straight wire. We know this law for straight wire, and if the distance of points A and B from the conducting wire in the stimulus is same, then in which point magnetic fields will be more? Give your opinion. That is mathematical opinion. Yes, we are talking about the magnetic field for a straight wire and a circular loop, and this is the law for a straight wire and circular loop. Now we are going to discuss about number C. If the wave P is turned into a circular loop, what will be the change of magnetic field? Analyze it mathematically. Okay, we are talking about the application of Biot-Savart law for a circular loop. So it is our circular loop equation, but we don't know about the radius. So it is our concern to find the radius. Okay, it is our concern to find the radius. Now we have to transform or turn this wire, that is P, into a circular loop. So this L should be equal to 2 pi R, and now L is replaced by 2 pi R. From here you will get very easily the value of R, and you can solve this math. Okay, let's say our next. Okay, This is our second stem. You look this stem, and it is the application of torque. So this is a rectangular bar or slab A, B, C, D. It is symbolized by A, B, C, D. Now let's see the question. Determine the magnetic moment of the coil. Magnetic moment is defined by M, and M is equal to NIA. So M is equal to NIA, that is N for number of turns, I current, and A is the area. Number B, if the coil is made a circle, how will its change of torque? Explain mathematically. Okay, at first we have to find out the torque for this loop, that is for this rectangular loop. Then we have to find out the torque for this coil or circular loop. Okay, for rectangular wire, we know tau is equal to NIAB, but for circular coil, we have to find out the area. Okay, for finding out the area, I have written here 2L plus B is equal to 2 pi R. From this, you can find out the R, and after getting out, you will get A is equal to pi R square, and then you will be able to find a difference between the torque of a rectangular wire and circular coil or wire. Now see, if the coil is deflected from the magnetic field at an angle 30, then find the torque. Okay, if this rectangular slab or coil is displaced at an angle 30, okay, so you will get your angle 30, but here you have to find out the angle. This angle between plane of normal and magnetic field, or if this angle between plane of the coil and magnetic field. Okay, plane of the coil and magnetic field. Here we are talking about the angle between magnetic field and plane of the coil. Between magnetic field and plane of the coil. That's why I have written here NIAB cos of theta. Okay, otherwise I have to write NIAB sine of theta. Otherwise I have to write NIAB sine of theta. Okay. Now for D, is it possible to calculate the work done to deflect the coil at an angle 90 degree? Yes, it is possible. We have to integrate this W is equal to tau is equal to tau d theta. Tau d theta. Okay. We have to integrate from 0 to pi by 2 or 90 degree. Okay. After solving this, we will get the amount of work done. Okay. For your betterment, I have solved it here. Okay. Okay, my dear boys, I think you will get clear concept about the application of torque and Weis-Schubert law. Please try to solve these questions that are inserted in your textbook. Okay. At a glance, what I have discussed today. I have discussed today terrestrial magnetism, magnetic material, and hysteresis loop. Types of questions. Firstly, knowledge-based questions and comprehension-based or understanding level questions are inserted here. Please have a look. Application level questions and higher order level questions are inserted here. Please have a look. Sample of MCQ are inserted here for the betterment of your understanding. Please have a look. Let's see the home task. This CQ is inserted or given here for your home task. Please, you should try your level best to solve this. If you face any difficult problem, please knock me. I'll try my level best to solve your question. Make 20 MCQ on the basis of my today's discussion, and assignment will be obtained on Thursday through our website. Please be attentive, be punctual about your online assignment. If you have any query, please ask me right now. I'll try my level best to solve your questions. Okay, my dear boys, thank you for attending my online class. We are passing through a very tough and rough situation. Corona is a pandemic. During the outbreak of this corona, please don't go outside of your home. Please stay home, stay safe. Pass quality time with your parents and family members. Be punctual about the online class and weekly assignment.